Good evening all. So today I'm just going to discuss about variational autoencoders. Okay. So what is variational autoencoder? The definition of variational autoencoder is nothing but it is a type of generative model. Okay. So this belongs to one type of generative model. We have already seen the different types of generative model. This comes under one type of generative model, and it uses encoder and decoder. Okay, so the purpose of the encoder is to learn the input, okay, to encode the input data into a compressed latent representation. So if we pass one input data, that will be converted to latent representation. Okay, so it will encode the given data to the latent representation. This is encoding part. Okay, in decoding part it reconstructed while also enabling sampling from the latent space. Okay, so input to the decoder is this
Sir,
latent
Lias is
sample
waiting outside. Please
representation.
let him inside, sir.
Okay, so this latent space will it will enable to so using this decode, okay, it will enable the sampling from the latent space to generate the new data. So the main aim of variational autoencoder is to generate the data as how this original image or original input data will look like. Okay, so same thing it is going to generate. Okay, so unlike we will be having traditional autoencoders also. Okay, but this variational autoencoders which will use the probabilistic distribution. Okay, it is used to model the data distribution explicitly. Okay, so the difference between the traditional autoencoder and this variation. Okay, so autoencoder it will just reconstruct the data, but in this variational autoencoder it will use it to generate the data. Okay, so what are the components of VAE? Okay, so we have encoder, latent sampling, decoder, and then loss. So these are four components in BAE. Encoder, first it maps the input X to latent parameters. Okay, so we have seen it, right? So this auto encoder will just use the input data and it will encode the input data into a latent representation. Okay, so encoder output will be the latent parameter. So what are those latent parameter is this mu. Okay, so this mu and then variance, okay, log variance. Okay, so the output of this one is the sampling, okay, and then this latent sampling and then mu and then log of sigma square. So these are our output of this encoder. Okay, so the second component is latent sampling. Okay, so this parameterization trick allows stochastic sampling with gradient computation. So here we will use the gradient operations. Okay, to minimize the losses. Okay. Then next part, so we will be having output of mu log sigma square and then latent sampling, okay, encoded output. And this output will be given to the decoder. So input, it maps latent variable, which is called as Z, okay. These all are Z, okay. So mu log sigma square and then this latent sampling, okay. Is that back to reconstruct the input X, okay. So X is the input, right? So this decoder it will reconstruct the X. Okay, so input images or input data will be reconstructed using this encoder and decoder. So variational autoencoder we will be having four component: encoder, latent sampling, decoder, and then loss. So loss, what is the loss of variational autoencoder means? It combines the reconstruction error. So we got this reconstructed output, right? So reconstruction error and then latent space regularization. So during this regularization also, we will get some loss. So if you combine both loss, you will get the loss of this VA. Okay. So encoder, it maps, so we'll see each component briefly. So the encoder maps the input data into a latent space. So this is the aim of this encoder. Instead of mapping to a single deterministic point, the encoder learns the probability distribution. it outputs two parameters. So the output of the encoder will be two parameter, mu and then log variance. Okay. So a vector mu is nothing but me. Okay. A vector representing the central tendency of the latent space distributions. So if you have one distribution, the mean of the distribution is nothing but latent space distribution. And then what do you mean by variance? A vector, this is also vector representation, a vector representing the spread of the latent space distribution. Okay, what is the variance? Okay, between the original and then represented form. Okay, so the encoder computes these parameters. So the final output of the encoder will be so normal distribution with this. This is the encoded output. Okay, so Z is the latent variable, and then mu x is the one output, and then log variance is the another output. So Q is the encoder computes. Okay, so Z of given x is the input. Okay, what is the Z of given x is nothing but normal distribution. Okay, so n represents the normal distribution of the given data, mu and then variance. Okay, so this is the output or encoder computes these parameters. So in latent, this is the second component in your variational autoencoder, latent space sampling. Okay, so what we are going to do means we will just do the gradient based optimization. That is nothing but back propagations. Okay. So once you compute it again, we have to do this gradient based optimization to fine tune it. Okay. A technique which is called as reparameterization trick. Okay. So here we are just doing or changing the parameter of the network. Okay. So is that equal to mu plus sigma of Ez? Okay. So where E of epsilon is nothing but random noise sampled from a standard normal distribution and element wise product, the symbol represents. Okay. This reparameterization. So in reparameterization, we are just using this one. Okay, mu plus sigma, and then each element just do the random noise sampled from a standard normal distribution. Apply the normal distribution. So it will enable the model to learn this mu and sigma while allowing stochastic sampling. Okay. The purpose of this latent space sampling, which will we are just doing this reparameterization trick. Okay, so that we can learn this parameter mu and sigma. Okay, so that we can reduce the loss, right? So these are the part and the encoding. And if you are going with the third component of VAE, that is nothing but decoder. Okay, in decoder, it takes the sampled latent variable, which is generated from the encoded part, and reconstruct the original input X. So here, original input is converted to latent stage representation, and then that one again given to the decoded part. Okay, decoded again use it to reconstruct it. Okay, so it models the likelihood. So here it will use the likelihood p of x by z. Okay, it's given z. Okay, so here input is z and the output is nothing but x. X is nothing but a original data, which is often assumed to follow a distribution like Gaussian or Bernoulli. So here we can use any Gaussian distribution or Bernoulli distribution. Depending on the data type, you can use the distributions. Okay, so that you can find the likelihood probability. Okay, so the decoder acts as the generative component of the VAE. So this we have encoded part and then decoded part. Okay, so you can use encoder to convert your input data into the latent space. Okay, so where you are doing this generative where you are just doing this generative data means in this decoder part. Okay, so this is decoder. So here only we are just generating the data. Okay, it produces realistic data samples when given a Z sampled from the prior distribution. So these are the Z value. Okay, so you can take any sample and it will give you the generated output. Okay. So, for example, once you consider one data set, it has some images. Okay. So you can train your variational autoencoders. Okay. So it will train the data. Okay. And finally, if you want to generate some data means, okay. So what I will give means just produce one image. Just that person is having some classes, okay, or cooling class or some. If you give some, if you give some descriptive, okay. So it will give you generation of new images, right? So based on the sample or based on how you have trained, you will get the good generative result. Okay. So in last
Ma'am,
question,
ma'am,
have to yes,
ma'am, my friend Thompson wants to join the meeting.
why?
Ma'am, it is asking to join.
No, I won't allow. Okay.
Okay, ma'am.
Mm. Loss functions, we will be having two loss functions, reconstruction loss and then pullback divergence law. Okay. So what do you mean by these two laws? So reconstruction loss, okay. So reconstruction loss, which will measure how well the reconstructed output matches with the input. Okay, so that is nothing but it reconstruct the given data. So if it is any error present during the reconstruction step, okay, that is considered as a loss of the functions. Okay, so it will just find the loss between the reconstructed output and the input. Okay, so here the function for the reconstruction is given. Okay, so here we will use typically you can use negative log likelihood, okay, or mean square error or cross entropy to find the loss. Okay, so many of you have used this one in machine learning also to find the loss, right? Next one, regularization. Okay, so we will do this regularization, right? So it KL divergence divergence laws. Okay, it regularizes the latent space by ensuring that the learned posterior distribution is close to the prior, okay, distributions. So these are the formula that is used to find the KL divergence loss. Okay. So what is the total loss of your VAE is nothing but total loss, which is equal to loss of VAE, which is equal to reconstruction loss and then KL loss. Okay. So in KL divergence and loss in VAE, which is used for regularize this latent space, okay, and then it encourages to smooth the function and continuity, okay, for sampling the input data, and it promotes the generalizations, okay. So once we have done it, we have to train the VAE. Okay. During training, the encoder and decoder are optimized jointly to minimize the total loss. So training is nothing but encoder and decoder both has to minimize the total loss. Okay. Total loss is equal to reconstruction loss plus KL loss. Okay. So the advantage of VAE is nothing but we can generate new samples by sampling from the latent space. So these words are very important. How we can generate means sampling from the latent space, we can generate the new data, and it provides a smooth structured latent space that facilitates interpolation and exploration. Okay. And it is very much useful in unsupervised learning, anomaly detection, and generative tasks. We are just using this VAE. So we have seen the different components in this class. Okay. So next class will see briefly about this video.